The morning of January 16, 1943, began like any other at the outfitting dock in Portland, Oregon. Workers arrived for the early shift at the Swan Island shipyard, their breath visible in the cold air, lunch pails in hand, ready for another day of fitting out newly launched Liberty ships. The vessels sat in the water awaiting final equipment installation, radios, lifeboats, navigation instruments, the 1,000 details that transformed a welded hull into a functioning cargo ship. Then someone noticed the SS Schenectady. The ship sat lower in the water than it should. Something was wrong with its silhouette. As workers moved closer, they saw what appeared to be a crack running along the deck. Then they realized it wasn't just a crack. The entire ship had split. The deck had torn open from one side to the other, a jagged fracture that ran down both sides of the hull all the way to the keel. The bow and stern sections had sagged, the midsection rising skyward like a broken spine. The ship had been floating peacefully at the dock. No storm had battered it. No torpedo had struck it. No cargo had overstressed it. The SS Schenectady had simply torn itself in half while sitting empty in calm water. Workers stood on the dock, staring. This ship had been launched just 2 months earlier. It had never carried a single ton of cargo. It had never faced a wave in anger. And yet there it was, catastrophically broken, its steel hull fractured as cleanly as if it had been made of glass. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The SS Schenectady was not alone. By January 1943, reports had begun filtering back from across the Atlantic. Liberty ships were developing cracks. Some cracks appeared in the deck. Others ran along the hull. A few ships had reported structural damage after storms. Then came worse news. The SS John P. Gaines had broken in half in the North Atlantic in November 1942, taking 10 men to the bottom. Other ships reported near catastrophic failures, saved only because they reached port before complete structural collapse. The United States was in the middle of the greatest shipbuilding program in human history. Liberty ships were the key to winning the war. They carried the fuel, ammunition, food, vehicles, and supplies that kept Allied armies fighting in Europe and the Pacific. German U-boats were sinking merchant ships faster than traditional construction methods could replace them. The solution had been revolutionary welding instead of riveting, prefabrication instead of piece-by-piece construction, assembly lines instead of individual craftsmanship. Henry Kaiser's shipyards had proven it could work. The SS Robert E. Peary had been assembled in 4 days, 15 hours, and 29 minutes. By 1943, Kaiser's yards were completing Liberty ships in an effortless average of 41 days, a pace unimaginable just 2 years earlier. Now those same ships were tearing themselves apart. The question was brutally simple. What was breaking the Liberty ships? The answer would reveal a truth about industrial warfare that no one wanted to hear, that America's greatest achievement in wartime production was simultaneously its most dangerous gamble, that the very innovation that allowed ships to be built so quickly had introduced a fatal flaw, and that the solution would require listening to a voice the maritime industry had spent decades ignoring. To understand what went wrong, you must first understand what went right. Before 1941, shipbuilding was a craft, not an industry. Ships were built from the keel up by crews of skilled workers who spent months on a single vessel. Riveters drove thousands of individual fasteners through overlapping steel plates, creating hulls that were strong but time-consuming to construct. Each rivet had to be heated until it glowed orange, inserted through precisely drilled holes in 2 or more plates, then hammered into place by a team of workers, a heater, a catcher, a bucker, and a riveter. The process was loud, labor-intensive, and slow. A traditional cargo ship took 6 months to a year to build. When war came to Europe in September 1939, this pace was inadequate. Britain needed merchant ships to replace losses to German U-boats. The United States needed to expand its merchant fleet to supply allies across both oceans. Traditional construction could not keep pace with the demands of global war. The solution came from an unlikely source. Henry J. Kaiser was not a shipbuilder. He had made his fortune constructing dams, the Hoover Dam, the Bonneville Dam, the Grand Coulee Dam. He understood concrete and steel, logistics and labour management, but he had never built a ship in his life. When the British government began contracting for cargo vessels in 1940, Kaiser saw an opportunity. He brought to shipbuilding the same mass production techniques that had revolutionized automobile manufacturing. The key innovation was welding. Instead of riveting overlapping plates, welders could join plates edge to edge by melting the steel and fusing it together. A good welder could create a joint stronger than the surrounding metal. More importantly, welding required far less skilled labor than riveting. A riveting team needed months of training and constant coordination. A welder could learn basic technique in a few weeks and work independently. Welding enabled prefabrication. Instead of building ships piece by piece at the dock, Kaiser's yards constructed entire sections, bow assemblies, stern sections, deck houses in separate workshops across the country. These prefabricated units, some weighing 250 tons, were shipped by rail to the shipyards. Massive cranes lifted the sections into position on the ways. Welders joined them, together. What had taken months could now be accomplished in weeks. The Liberty ship design itself was deliberately simple. Based on a British tramp steamer design, the Liberty ship was 441 feet long and 57 feet wide. It had a single steam engine, a simple triple expansion design that was obsolete but easy to manufacture. The cargo holds were vast and uncluttered. The accommodations were basic. Everything about the ship prioritized speed of construction and simplicity of operation over comfort or sophistication. By 1942, Kaiser had built 7 shipyards on the West Coast, 4 in Richmond, California, and 3 along the Columbia River in Oregon and Washington. The Richmond shipyards alone employed 90,000 workers at their peak. The workforce included men too old for military service, teenagers, African Americans migrating from the South, and thousands of women who had never worked in heavy industry. The women who welded Liberty ships became icons of American industrial power. They were called Rosie the Riveters in popular culture, though most actually welded rather than riveted. They were Wendy the Welders in the shipyards themselves. They came from every background imaginable: housewives, teachers, waitresses, farm workers, all responding to the urgent call for labor. Mary Carroll was 50 years old when she applied to Kaiser Richmond Shipyard in 1942. She had lost her 27-year-old son in the Battle of Bataan in the Philippines. She wanted to contribute to the war effort in his memory. She became the first female shipyard welder at Kaiser, learning to strike an arc, maintain a bead, and join steel plates with sufficient strength to hold back the Atlantic Ocean. On July 19, 1942, she received recognition for excellence in production when Rear Admiral Howard L. Vickery presented the shipyard with an award for speed and efficiency. Louise Cox had learned acetylene welding from her father as a child, working in the family garage in Tennessee. She studied metallurgy and music at the University of Tennessee, an unusual combination that reflected her unusual mind. When her brother joined the Navy, she took his place on the production line at Kaiser Richmond Shipyard No. 2, becoming the first woman welder trainee there. She understood the science of what she was doing, the heat-affected zones and grain structures and fusion properties that most welders never thought about. When she wasn't working, she designed women's welding clothes that emphasized safety, understanding that the standard men's welding gear left women vulnerable to burns and hot metal. Gladys Theus became known as the fastest welder at Kaiser Richmond in 1944. Eastine Cowner, formerly a waitress, worked as a scaler, grinding and preparing welded surfaces for painting. Precious Mack moved from Shreveport, Louisiana, with her family, living in a trailer until they found wartime housing. These women, and thousands like them, worked in conditions that would be considered brutal by modern standards. The noise was deafening, cranes creaking, metal clanging, arc welders crackling. The heat was oppressive, especially inside confined spaces in ship hulls. The work was dangerous. Arc flash could blind, hot metal could burn, heavy sections could crush, but the pay was good. Women earned the same wages as men for the same work, an equality virtually unheard of in 1942 America. More than money, the work provided purpose. Every ship they built carried supplies that kept soldiers alive, that sustained armies, that enabled the fight against fascism. The women knew this. Many had husbands, brothers, sons in combat. They realized that lives depended on the quality of their welds. The training was brief but intense. New workers received a few weeks of instruction on welding technique, safety procedures, and quality standards. They learned to read blueprints, operate equipment, and inspect their own work. Then they went onto the production line. Some worked in shops, welding deck sections and bulkheads in climate-controlled spaces. Others worked inside ship hulls, crawling into bilges and double bottoms, welding in positions where they could barely move, breathing air thick with metal fumes. The pace was relentless. By the fall of 1943, Kaiser Richmond was completing one Liberty ship every single day. At peak production, the 4 Richmond yards launched 3 ships in one day. Workers saw immediate results from their labor. A ship they had worked on one week would be in the water the next, being fitted out, preparing to sail into harm's way. By early 1943, the scope of the problem was becoming impossible to ignore. The United States Coast Guard, responsible for merchant vessel safety, established a board of investigation in April 1943 to examine the construction, design, and fractures of welded ships. The investigation would span 3 years and examine thousands of reports. The numbers were sobering. By April 1, 1946, when the board published its final report, it documented that 970 of the 4,694 merchant ships welded during the emergency shipbuilding program had sustained fractures. Nearly 1 in 5 ships had experienced significant structural cracking. Of the 2,710 Liberty ships built, 12 had broken completely in half. 3 of those catastrophic failures occurred in Liberty ships. Hundreds more had suffered serious damage cracks that propagated through decks, along hull sides, around hatches. The SS John P. Gaines went down on November 24, 1942, in the North Atlantic, taking 10 lives with it. The ship had simply split in 2 in heavy seas. The SS SO Manhattan, a 2-tanker, broke in half. On March 9, 1943, the crew abandoned ship, and both sections remained afloat long enough for rescue. The Fort Mercer, another 2-tanker, split in half during a winter storm in February 1952, years after the war ended. The Pendleton broke in half during the same storm. These were not isolated incidents. They were symptoms of a fundamental flaw in the ship's construction. The initial suspicion fell on the welders. This was, after all, a new technology being implemented at unprecedented scale by largely inexperienced workers. The narrative was convenient and fit existing prejudices. The shipyards had hired thousands of women and minorities, people who had never worked in heavy industry. Surely these inexperienced workers were creating defective welds. Newspaper articles speculated about Wendy the welder, making mistakes that cost lives. Union officials complained that wartime hiring practices had lowered quality standards. Naval architects suggested that welding itself was inherently inferior to riveting for ship construction. The Coast Guard investigation examined welds carefully. Metallurgists cut sections from failed ships and studied them in laboratories. They found some defective welds inclusions, porosity, incomplete fusion, but these defects were not consistent enough to explain the pattern of failures. Many ships with similar weld quality never cracked. Many of the catastrophic fractures did not originate at welds at all. Investigators noticed something else. The failures occurred predominantly in cold weather. Ships operating in the North Atlantic were far more likely to crack than ships in the Pacific or Mediterranean. The SS Schenectady had failed in January in Portland, Oregon, where temperatures hovered near freezing. Other ships reported cracks after passing through winter storms. The temperature correlation was undeniable but unexplained. The steel itself became a focus of investigation. Liberty ships were built from ordinary mild steel, the same material used for countless structures. The specifications called for steel, with a tensile strength of 50 to 60,000 pounds per square inch, carbon content around 0.2%, and various other elements in small quantities. Nothing about these specifications seemed unusual. Thousands of bridges, buildings, and earlier ships had been constructed from similar steel without problems. But the manufacturing process during wartime was far from ideal. Steel mills were operating at maximum capacity, producing material as quickly as possible. Quality control was minimal. The chemistry of the steel varied from heat to heat, batch to batch. Some plates had higher sulfur content than specifications allowed. Others had insufficient manganese. The ratio of manganese to sulfur, which affects how steel behaves under stress, varied widely. The pouring, rolling, and shaping processes left an undesirable chemistry in many plates. Sulfur content was too high. Manganese content was too low. These impurities, which would cause only minor problems in most applications, had catastrophic consequences in welded ship construction. The steel's microstructure, the arrangement of crystals and grains invisible to the naked eye, determined how it would behave at different temperatures. Investigators conducted Charpy V-notch tests on steel samples from failed ships. This test measured how much energy the steel could absorb before fracturing when struck by a weighted pendulum. The results were alarming. Plates from Liberty ships had widely varying properties. Some performed well even at cold temperatures. But 90% of the samples tested had what metallurgists call a ductile to brittle transition temperature at or above 7 degrees Celsius, 45 degrees Fahrenheit. Below this critical temperature, the steel's fracture behavior changed fundamentally. At normal temperatures, steel is ductile. When stressed, it deforms, gradually, bending and stretching before eventually tearing. This ductile behavior gives warning. Cracks grow slowly. Structures sag visibly before failing, but below the transition temperature, steel becomes brittle. When stressed beyond its limit, it fractures suddenly, without warning, without visible deformation. Cracks propagate at speeds up to 3,000 feet per second. A fracture that starts at one point can race across an entire ship hull in seconds. The North Atlantic frequently had water temperatures below 7 degrees Celsius, especially in winter. Ships operating in those conditions were running on steel that had transformed from ductile to brittle. Any stress concentrator, a square hatch corner, a welding defect, even a small nick in the surface could initiate a crack. And once a crack started in the brittle steel, nothing could stop it. While American investigators struggled to understand the failures, the British Admiralty Ship Welding Committee engaged a metallurgist at Cambridge University to lead their investigation. Her name was Constance Tipper, and she would discover what everyone else had missed. Constance Fligg Elam was born in February 1894 in New Barnet, Hertfordshire. She studied engineering at Newnham College, Cambridge, starting in 1912, becoming one of the first women to take the natural sciences tripos. This was a time when women were barely tolerated in engineering, when their presence in laboratories and classrooms was considered a novelty at best, an intrusion at worst. She graduated with a third-class degree, not brilliant, but sufficient to launch a career in research. In 1915, she joined the metallurgical department of the National Physical Laboratory in Teddington. The following year, she moved to the Royal School of Mines, where she was appointed research assistant to Sir Harold Carpenter. In 1921, she was elected to the Fresherville Research Fellowship. Her early research focused on the behavior of metal crystals under stress, work that would later inspire developments in dislocation theory. In 1923, working with the famous scientist Geoffrey Ingram Taylor, she received the Royal Society's Bakerian Medal for research on the distortion of aluminum crystals under tension. The Royal Society initially did not realize that C.F. Elam was a woman. When the award ceremony came, she was informed she could not attend the celebratory dinner. The Royal Society did not permit women. In 1928, she married George Tipper, a graduate of Clare College and superintendent of the Geological Survey in India. She took his name and continued her work. In 1929, she left the Royal School of Mines with a doctorate and settled in Cambridge, where she would work for the next 3 decades. When war came in 1939, Tipper was appointed as a lecturer in the Department of Engineering at Cambridge, one of the first women lecturers in the university. Many male lecturers had left for wartime work. The university needed her expertise. In 1943, when Liberty ships began breaking in half, Professor John Baker in the engineering department was asked to investigate. He asked Tipper to lead the metallurgical analysis. Tipper approached the problem methodically. She obtained steel samples from ships that had failed plates cut from the SS Ocean Vulcan, the Empire Duke, and others. She conducted extensive testing, measuring the steel's properties at different temperatures. She used microscopy to examine the grain structure. She analyzed the chemistry, documenting sulfur content, manganese levels, carbon percentages, and trace elements. What she discovered contradicted the prevailing assumptions. The welds were not the problem. In fact, most of the catastrophic fractures had not originated in welds at all. They started in the base metal, the steel plates themselves. The fractures then propagated through the welds and continued into adjacent plates. But the welds were not the initiating cause. The problem was the steel's transition temperature. Below a critical point, the material changed from ductile to brittle. Tipper demonstrated this phenomenon with elegant simplicity. She tested identical steel samples at different temperatures. At room temperature, the samples bent and deformed when struck. At cold temperatures, they shattered like glass. The difference was not in the steel's chemical composition or the quality of its manufacture. The difference was purely temperature. This was revolutionary. Everyone knew that some materials became brittle when cold cast iron, for instance, was notoriously fragile at low temperatures. But mild steel was supposed to remain ductile. It was used for bridges in Canada, for storage tanks in Siberia, for countless applications where cold temperatures were routine. The idea that ordinary ship steel could become brittle in min conditions regularly encountered in the North Atlantic was shocking. Tipper went further. She investigated why some steel plates had lower transition temperatures than others. She found that chemistry mattered enormously. High sulfur content raised the transition temperature, making steel more likely to become brittle at temperatures ships would encounter. Low manganese had the same effect. The ratio between these elements was critical. Steel with good manganese to sulfur ratios remained ductile at much lower temperatures. She also discovered that the manufacturing process affected transition temperature. How the steel was rolled, whether it was heat-treated, how quickly it cooled, all of these factors influenced the grain structure, and thus the temperature at which ductile behavior gave way to brittle fracture. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Tipper developed a test to measure the ductile brittle transition temperature of steel samples. The test, which would become known as the Tipper test, involved striking notched samples with a weighted pendulum at various temperatures and measuring the energy absorbed. By plotting the results, she could determine the temperature below which a particular steel would behave in a brittle manner. The implications of Tipper's findings rippled through the shipbuilding industry like the cracks through Liberty ship hulls. The welders were not to blame. The women who had been accused of careless work, the inexperienced labourers who had been suspected of introducing defects, they had done their jobs correctly. The problem lay in the material itself, in decisions made by steel mills and procurement officers who had no idea they were creating a fatal flaw. The revelation was both vindicating and devastating. Vindicating because it proved that the workers, especially the women who had faced so much skepticism, had not failed in their duties. Devastating because it meant that hundreds of ships already at sea were sailing with hulls made of steel that could turn brittle in cold water. Every Liberty ship operating in the North Atlantic was potentially vulnerable. Every winter storm could trigger a catastrophic failure. The British government moved quickly on Tipper's findings. The Ministry of War Transport borrowed the British-built Empire Duke for comprehensive testing. Tipper and her team subjected the ship to cold temperatures while monitoring its structural behaviour. They confirmed that the steel changed properties at critical temperatures. They documented how cracks could initiate at stress concentrations, square hatch corners were particularly problematic, and then propagate catastrophically through brittle steel. The American investigation, working independently but arriving at similar conclusions, published its final report in 1946. The Board of Investigation confirmed that the failures were caused by a combination of factors. First, the steel had poor Charpy impact-tested fracture toughness at low temperatures. Second, the all-welded construction created a continuous structure where cracks could propagate unimpeded, unlike riveted ships where cracks would stop at plate boundaries. Third, stress concentrations at square hatch corners and other design features provided initiation sites for fractures. But the primary cause was the steel's ductile brittle transition. The report stated that plates from Liberty ships, which had experienced brittle failures, had transition temperatures ranging from 15 to 65 degrees Celsius, with a mean of 40 degrees Celsius. This steel would be notch brittle during winter and spring in the North Atlantic. The specifications in use had not been sufficiently selective to exclude such steel. The solutions were relatively straightforward once the problem was understood. Steel quality needed improvement. Sulfur and phosphorus content had to be reduced. Manganese levels had to be raised. The manufacturing process required better control to produce steel with lower transition temperatures. Design changes were needed. Square hatch corners were replaced with rounded corners to eliminate stress concentrations. Crack arresters were installed, riveted straps placed at critical points to stop propagating cracks before they could tear a ship in half. These measures were implemented in the Victory ships, the improved design that succeeded the Liberty ships in 1944. The Victory ships used the same steel as Liberty ships, but incorporated design changes based on the failure investigations. Frame spacing was widened from 30 inches to 36 inches, making the ships less stiff and more able to flex with wave motion rather than accumulating stress. The rounded hatch corners and crack arrestor straps prevented the catastrophic propagation seen in Liberty ships. Existing Liberty ships were retrofitted where possible. Ships received reinforcing straps welded around hatch corners. Additional plating was added in high-stress areas. Ships operating in cold waters received extra inspections. Cracks were detected early and repaired before they could propagate to catastrophic failure. The irony was profound. The United States had mobilized its industrial might to produce ships at a rate never before achieved in human history. The assembly line techniques, the prefabrication, the welding technology, all of it worked exactly as designed. The workers, including the thousands of women who had been doubted and blamed, had performed their jobs with skill and dedication. The ships were built quickly, efficiently, and to specification, but the specifications were wrong. The steel that seemed perfectly adequate for normal construction was dangerously unsuitable for welded ships operating in cold water. This was not a failure of American industrial capability. It was a failure of metallurgical understanding. In 1941, when the Liberty ship program began, no one fully understood ductile brittle transition. The science of fracture mechanics was in its infancy. The Charpy impact test existed but was not routinely used for ship steel specifications. Despite the failures, the Liberty ship program was an overwhelming success. The statistics tell a story of industrial mobilization on a scale that had never been attempted before and has never been matched since. 2,710 Liberty ships were built between 1941 and 1945. They carried more than two-thirds of all cargo leaving the United States during the war. They transported fuel to keep tanks moving, ammunition to keep guns firing, food to keep armies fed, medicine to keep soldiers alive, and equipment to keep the war machine functioning. The losses, while tragic, were statistically small. Of the 2,710 ships built, 12 broke completely in half. Hundreds suffered cracks, but most of these were repaired and the ships returned to service. The vast majority of Liberty ships performed exactly as intended. They crossed the Atlantic through U-boat-infested waters. They sailed to Murmansk on the deadly Arctic convoys. They supplied the invasions of North Africa, Sicily, Italy, and Normandy. They kept island-hopping campaigns in the Pacific, sustained with fuel and supplies. Many Liberty ships survived not just the war, but decades of peacetime service. The SS John W. Brown, launched in September 1942 from Baltimore, Maryland, is still operational today. Restored by volunteers, she serves as a museum ship and occasionally steams on Chesapeake Bay, her triple expansion engine still turning, her welded hull still sound after more than 80 years. The SS Jeremiah O'Brien, built in Portland, Oregon, in 1943, still operates from San Francisco. She returned to Normandy in 1994 for the 50th anniversary of D-Day, making the crossing under her own power, a testament to the fundamental soundness of the design. The ships that did fail taught lessons that transformed naval architecture and materials science. The catastrophic brittle fractures of Liberty ships led directly to the modern field of fracture mechanics. Engineers developed new tests, new specifications, new design principles. The drop weight test, developed in the late 1940s, provided a standardized method for determining the nil ductility transition temperature of steel. This test became mandatory for ship steel and later for other critical applications: pipelines, pressure vessels, bridges, buildings. Steel manufacturing improved dramatically. Mills learned to control sulfur and phosphorus content more carefully. Heat treatment processes were refined to produce finer grain structures and lower transition temperatures. By the 1950s, structural steel was reliably ductile at temperatures far below 0 degrees Celsius. The brittle fractures that plagued Liberty ships became increasingly rare in new construction. Design principles changed. Naval architects abandoned square corners in favor of rounded transitions. Stress analysis became more sophisticated, with engineers calculating stress concentrations and designing structures to minimize peak stresses. The concept of crack arresters, features deliberately designed to stop propagating cracks, became standard in critical structures. Welding codes were established and continually refined. The American Welding Society, the American Society of Mechanical Engineers, and other organizations developed detailed specifications for welding procedures, welder qualification, and inspection methods. Welders received better training. Inspectors used radiography and ultrasonic testing to detect internal defects. The quality of structural welding improved dramatically, but perhaps the most important legacy was the validation of women in industrial work. The women who welded Liberty ships proved they could perform skilled technical work at the highest levels. Mary Carroll, Louise Cox, Gladys Theus, Eastine Cowner, and thousands of others demonstrated that gender had nothing to do with capability. When investigators discovered that the fractures were not caused by welding defects, it vindicated every woman who had faced suspicion and blame. After the war, most women were pushed out of industrial jobs as returning servicemen reclaimed positions. The cultural narrative of Rosie the Riveter was celebrated in retrospect, but at the time, women were expected to return to domestic roles. Yet something had changed. Women had tasted independence, earned substantial wages, performed work that mattered. The experience would fuel the women's rights movements of subsequent decades. Constance Tipper continued working at Cambridge University until her retirement in 1960. She was appointed Reader in 1949, becoming the only full-time woman member of the Faculty of Engineering. After retirement, she worked as a consultant on metallurgy in submarine construction in the northwest of England. She published over 80 papers during her career. Her book, The Brittle Fracture Story, published in 1962, became a definitive work on the subject. Part 8, Aftermath and Legacy. The scale of achievement. The Liberty ship program, even with its failures, remains the most impressive industrial achievement of World War II. The numbers are staggering. 2,710 ships in 4 years. That's an average of 1 ship completed every day and a half for 4 years straight. At peak production, American shipyards launched 3 ships per day. To put this in perspective, consider the construction time evolution. The SS Patrick Henry, the first Liberty ship, was launched in September 1941, after 150 days of construction. By late 1942, the average had dropped to 70 days. By 1943, Kaiser's Richmond yards were averaging 41 days. The SS Robert E. Peary's 4-day construction time was a publicity stunt. Much of the fitting-out work remained after launch, but even accounting for complete construction, the pace was extraordinary. The human effort behind these numbers is equally impressive. At peak employment, The 4 Richmond Kaiser shipyards employed 90,000 workers. Across all American shipyards building Liberty ships, hundreds of thousands of people worked around the clock in 3 shifts. They consumed mountains of steel. Each ship required approximately 10,000 tons of steel plate, shaped, cut, and welded into hull sections, decks, bulkheads, and superstructure. The welding alone was prodigious. Each Liberty ship required approximately 150,000 individual welds. Multiply that by 2,710 ships, and American welders created more than 400 million welds during the Liberty ship program. The vast majority of these welds were sound, meeting or exceeding specifications, performed by workers who learned their craft in a few weeks and then practiced it under intense production pressure. The prefabrication infrastructure was a logistical marvel. Components were manufactured in 250 facilities across the United States. A bow section built in Chicago would travel by rail to Richmond, California. An engine assembled in Ohio would ship to Portland, Oregon. Deck sections, hull plates, bulkheads, piping assemblies, ventilation systems, electrical components, all moved across the continent on precisely timed schedules to arrive when needed for assembly. The steel itself came from mills working at absolute capacity. American steel production increased from 28 million tons in 1939 to 89 million tons in 1944. Blast furnaces operated continuously. Rolling mills ran 3 shifts. Quality sometimes suffered under the pressure, hence the sulfur and manganese problems that led to brittle fractures. But the sheer volume of production enabled not just the Liberty ships but tanks, aircraft, ammunition, and countless other war materials. The economic mobilization was unprecedented. The United States spent approximately $350 million on the initial Liberty ship program. Each ship cost between $1.5 and $2 million to build, expensive, but not prohibitively so. More importantly, a Liberty ship only needed to make one successful voyage to be considered economically worthwhile. If it carried 10,000 tons of cargo across the Atlantic once and then was sunk by a U-boat, it had still delivered supplies that cost far more than the ship itself. Many Liberty ships made dozens of voyages. They sailed in convoys, protected by destroyer escorts and aircraft, facing constant threat from U-boats but usually arriving safely. The U-boats did sink many Liberty ships. German submarines were frighteningly effective in 1942 and early 1943. But American shipyards were building ships faster than U-boats could sink them. By mid-1943, the tide had turned. Improved convoy tactics, better anti-submarine weapons, and the sheer number of available ships meant that supplies flowed across the Atlantic in ever-increasing quantities. The Germans understood what this meant. They watched American production figures with growing alarm. German industry, even with slave labor and captured factories across occupied Europe, could not match American output. German shipyards built U-boats as quickly as possible. 1,162 were commissioned during the war. But the U-boats were sunk faster than they could be replaced, while American merchant ships multiplied. By 1944, the Battle of the Atlantic was effectively over. American industrial capacity had won. Part 9, Aftermath and Legacy, The Truth About Victory. Return to that morning in January 1943, the workers standing on the Portland dock, staring at the SS Schenectady broken in half. They did not know they were witnessing the birth of modern fracture mechanics. They did not know that a woman scientist at Cambridge University would solve the mystery. They did not know that their work, despite this visible failure, was winning the war. All they knew was that something had gone terribly wrong. A ship had broken. Lives might be lost. Their work might be blamed. For the women welders especially, this moment was frightening. They had faced skepticism from the beginning. Many men in the shipyards resented their presence. Union officials had opposed their hiring. When ships started cracking, the whispers started: inexperienced workers, inadequate training, women who couldn't handle the work. Constance Tipper gave them vindication. Her meticulous research proved that the welding was not the problem. The women who had been blamed were not at fault. They had done exactly what they were trained to do. They had created welds that met specifications. The specifications themselves were inadequate, but that was not the welder's fault. It was a failure of metallurgical science, not of industrial workmanship. This distinction mattered then and matters now. When complex systems fail, the temptation is always to blame the operators, the workers, the people most visible in the process. But often, as with the Liberty ships, the failure lies deeper in design assumptions, in material properties, in knowledge that simply did not exist at the time decisions were made. The Liberty ship program succeeded because it was flexible enough to learn and adapt. When ships cracked, investigators studied the failures rather than simply assigning blame. When Constance Tipper and American metallurgists identified the steel problem, the industry changed specifications. When designers recognized stress concentrations at hatch corners, they modified the design. The Victory ships incorporated these lessons. Existing Liberty ships were retrofitted. The problems were solved. This adaptability, this willingness to confront failure and learn from it, was as much a part of American industrial strength as the production numbers. The Soviet Union built ships during the war but could not match American quality or quantity. German industry produced impressive weapons but could not scale production efficiently. Japanese industry, starved of raw materials and unable to mechanize effectively, fell further behind with each passing year. Britain's industry, devastated by bombing and limited by resources, depended on American production. The United States combined massive industrial capacity with scientific rigor and practical problem-solving. When a problem emerged, brittle fracture in ship steel, American and British scientists investigated systematically, identified the cause, and implemented solutions. This process, repeated across countless war production programs, is why the Allies won. The Liberty ships themselves are now mostly gone. Many were scrapped after the war, some were sunk as targets, a few were converted to other uses. The two surviving operational examples, John W. Brown and Jeremiah O'Brien, serve as floating museums, preserving the memory of the program and the people who made it possible. But the lessons learned from Liberty ship failures persist. Every modern ship is designed with fracture mechanics in mind. Every bridge, every pressure vessel, every critical structure uses steel specified to remain ductile at the temperatures it will encounter. Engineers routinely calculate stress concentrations and design features to prevent crack propagation. Welders follow detailed codes developed from decades of experience and research that began with investigating why Liberty ships cracked. And the International Congress on Fracture awards the Constance Tipper Silver Medal to mid-career scientists and engineers who make significant contributions to understanding fracture. The award honors the woman who proved that blaming workers is easier than understanding materials, that solving problems requires careful science rather than convenient scapegoats, and that sometimes the most important contributions come from voices the establishment would prefer to ignore. The SS Schenectady, broken in half at the dock in January 1943, was repaired and returned to service. She sailed until after the war ended, carrying cargo across oceans, surviving storms and threats, her welded hull holding together despite the flawed steel from which she was built. She was finally scrapped in 1947, having served her purpose, having survived her flaws, having contributed to victory despite the fear and confusion of that morning when she split. That is the story of the Liberty ships, not a story of perfect engineering or flawless production, a story of massive achievement despite inevitable problems, a story of workers doing their best with imperfect knowledge, a story of scientists solving puzzles others wanted to ignore, a story of victory won not through perfection but through scale, adaptation, and persistence, a story of ships built so quickly they launched almost daily, carrying supplies that won a war, cracking sometimes but sailing more often, flawed but functional, imperfect but sufficient. The women who welded them knew their work mattered. The men who designed them learned from their failures. The scientist who explained why they cracked advanced human knowledge. And the ships themselves, rushed into service with fatal flaws hidden in their steel, sailed anyway and delivered victory. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.